Hey everybody, we're going to continue this lecture series now on what we started as ADME, properties, pharmacokinetics. We did a little bit on the use of radioactive compounds to analyze metabolites, or radioactively labeled compounds and radioactively labeled drugs and metabolites. We also did a little bit on this radioactively labeled compounds used to create imaging agents for positron emission tomography, which is shown with this mouse here. But now we're actually moving on to metabolism and all the different metabolic pathways that are found in our bodies. Okay, so what we're going to do now is talk about metabolism and review the concept of phase 1 metabolism and also phase 2 metabolism. There's a couple different enzyme systems. There's cytochrome P450, which we've mentioned before. It's one of the key metabolic systems. Flavins, which do a certain kind of oxidative metabolism. And also soluble enzymes, which do another type of reaction, usually not oxidative, but maybe hydrolysis of stuff, hydrolysis of amides or esters. Oh yeah, and then then what we'll do is we'll go into the different transformations, oxidation, and really an important one called oxidative dealkylation. So this is like an oxidation reaction that's coupled with a dealkylation, so maybe loss of a methyl or something like that. And kind of a little bit on the mechanism of those. And we'll talk about reduction, so some reactions that cause reduction of an organic molecule. Hydrolytic metabolism, which would mean hydrolysis of an ester or amide or something like that. Then we'll talk about phase 2 transformations, which are the kind of conjugations that happen, maybe addition of a glycine or a glucuronic acid or some kind of things that get attached to your molecule. Okay, so the function of drug metabolism is to transform foreign compounds, we call them xenobiotics, which is just anything that enters our body, into water-soluble derivatives, which can be readily eliminated by the kidneys. Why do we have this function in our bodies? I think if you consider evolution, our bodies are probably always afraid of foreign substances, right? And anything that enters our body must be eliminated or removed, and that's probably what happened, through an evolutionary sense. And then of course now we have drugs that are supposed to be doing something positive to the body, and so oftentimes we're trying to evade the metabolic processes. Okay, so if you have small volatile metabolites, CO2, amines, alcohols, thiols, or even like gaseous anesthetic type drugs, they can be actually eliminated through the lungs. Often, though, things get excreted through the kidneys or maybe through the colon in feces. There's 2 phases of drug metabolism, phase 1 and 2, and we have talked about these a little bit. Here's an example. So this is propoxyphene or Darvon. It's an analgesic, painkiller. And so phase 1 metabolism would remove one of the methyl groups and then phase 2 would replace the methyl ultimately with this thing called a glucuronic acid. And glucuronic acid is one of the conjugates that occurs during phase 2 metabolism. And then now you've made your drug molecule very polar, and the kidney is really good at excreting these kind of things. This is like a sugar almost, right? Okay, so let's get into phase 1 metabolism. it introduces or reveals functional groups that help drug excretion. The three types that we will discuss are oxidation or oxidative metabolism. Specifically, oxidative dealkylation is seen a whole bunch, and we'll see that, several examples of that. Reductive alkylation, maybe like a ketone to an alcohol, and also hydrolytic reactions, and that is hydrolysis of an amide or ester. And phase 2 metabolism, we will attach different conjugating molecules to our drug to improve its excretion. Glucuronide, which is what we just saw, is the sugar type thing. It's then in the actual conjugating molecule is called glucuronic acid. And we can also attach sulfate. We can attach amino acids. Often glycine or glutamine is found. Glutathione, which we've seen before, is it's a scavenger for biological electrophiles. It's based on cysteine, so it's got a sulfur, and it will attack in an SN2 manner. Acetate and methyl are a couple of the other ones. And the result of phase 1 and phase 2 transformations is usually inactivation or detoxification. Obviously, if it's a beneficial drug, then you wouldn't really say it's detoxifying it, but certainly for toxins and toxic molecules that we might ingest, these transformations would detoxify it. And the other thing is, like we've said before, sometimes a drug is designed so that its metabolism improves its pharmacokinetic properties, and that's what we call a prodrug. So a prodrug is something that is maybe inactive initially, gets metabolized, then becomes a pharmacologically active drug. Here's one example. So this is naltrexone. This is naltrexone 3-salicylate, and we've talked about naltrexone. It's an opioid antagonist, and so it binds to the opioid receptor and prevents its activity. Anyway, so this is a prodrug, and it basically has aspirin conjugated to it. So this is aspirin, and the aspirin's not really there to do anything. It's just kind of like a placeholder that can be hydrolyzed by first pass metabolism and probably an esterase, something that cleaves this ester, and then that liberates aspirin and naltrexone. In this case, this prodrug, and I don't think it's actually used commercially, but it was definitely reported in the literature, it's 30 times more orally bioavailable than the product, meaning naltrexone. So this prodrug can be administered orally and is much more bioavailable and more active ultimately. So there's 3 classes of metabolic systems that affect phase 1 metabolism. The first are the cytochrome P450 enzyme family members. They're present in most tissues, but there's really found in liver. So a lot of these phase 1 metabolic reactions occur in the liver. They contain heme, and heme contains iron, and iron allows some really cool types of reactivity that are maybe less familiar in biological reactions and enzyme reactions. And there's different isoforms of P450, 3A4, 2D6, 2C9, 1A2. We're not going to talk about each isoform really specifically. In a real drug discovery project, it turns out that some drugs will actually inhibit different isoforms of these and cause drug interactions with other drugs. I think we've talked about that before a couple times also, and so sometimes it's a juggling act of having your drug of action be active and be metabolized maybe by one of these isoforms, but then having another drug also inhibit maybe one of these other isoforms, and then you have drug interactions. So there's some concern about that when we administer drugs in a clinical setting. Okay, P450 can catalyze oxidation and reduction reactions. And then we also have the flavin-dependent monooxygenases, FMO. So these often will directly oxidize like a nitrogen or sulfur. So a nitrogen will, in an amine, nitrogen with 3 things on it, will get an extra oxygen added onto it. So it becomes an amine oxide, like an NO type thing. And sulfur does that also. Sulfur can be directly oxidized by FMO. For the most part, I should say that FMO does that, this direct oxygenation, whereas P450 does these kind of other things that we'll see, like the oxidative dealkylation. P450 usually does not directly oxygenate an atom like sulfur or nitrogen. There will be exceptions to that. But I should also say P450 often oxidizes carbon, for example. So P450 might oxidize carbon, whereas FMO might directly oxygenate things like nitrogen and sulfur. Hopefully that'll be a good preview of the reactions we'll see. And then we also have another class of enzymes, like a third class of enzymes called esterases and amidases. And you can guess what they are going to do. They are going to cause hydrolysis reactions of esters and amides and things like that. Okay, so the P450 heme proteins have a pretty well characterized reaction mechanism. And we'll kind of step through it. It's a catalytic cycle. Looks a little crazy, but it's not that crazy. So P450 Fe3+ kind of refers to the protein with its heme in it, and it has an iron 3+ in it. And iron 3 and iron 2 can sort of go back and forth. They can be oxidized and reduced. So they're used in sort of electron transport mechanisms. Okay. Kind of coming into the catalytic cycle is RH, which is our molecule, our substrate for P450, which will be oxidized. And coming out will be ROH, so that'll be the oxidized form of a molecule. So they're ultimately oxidizing the molecule from RH to ROH. Okay, and so coming into this mechanism, NADPH and NADH, which are biological reducing agents, they will turn over and convert FAD in its oxidized form to its reduced form. So NADH and NADPH are going to act as a reducing agent here, and that's going to reduce FAD to FADH2. And then FADH2 is going to turn over in this direction. FADH2 is a reducing agent, and it's going to reduce iron 3+ in the P450 reductase, which is a different enzyme, from iron 3+ to iron 2+. And then iron 2+, which is in a low oxidation state, will kind of act as a reducing agent, which will reduce iron 3+ in the P450 complex, and now P450 has our substrate sort of conjugated into it, and iron 3+ will be reduced to iron 2+. And then oxygen will enter the mix, and oxygen will ultimately be the oxidizing agent that oxidizes our molecule. But currently, at this point, P450 is in its low oxidation state with iron 2+. Oxygen gets incorporated and complexed to the heme, into the iron, and it sort of attaches like this. So now we have P450, iron 2+, the substrate is attached, and we have oxygen kind of attached. And then there's another reduction step with NADPH and NADH, which will reduce. It does a two-step thing. It reduces the oxygen, and kind of through another step, it also oxidizes iron. So a couple things are happening in this process. And you have when oxygen is attached in this way, NADH and NADPH cause two things: reduction of the oxygen and oxidation of the iron. And this all happens through the coordination of NADH and NADPH and the oxygen and the iron. So now you have this this intermediate in the mechanism. Water gets lost. Now you have an oxygen attached to your iron, and then through another kind of magical reaction, the oxygen that's on the iron gets transferred over to the substrate. So there's more detail to this mechanism, but this kind of shows how some of the cofactors are involved, like NADH and NADPH, how oxygen is involved, and how ultimately the substrate is converted to the product. And this is probably okay to understand a little bit without going into the details of this mechanism. I think the detailed mechanism is a little crazier. Okay, so let's get into the transformations now. The reactions. We'll start with oxidation, phase 1 oxidation, and also oxidative dealkylation. Okay, so what kinds of oxidation reactions might occur? So oftentimes it will incorporate a hydroxy group into a molecule, and that'll aid in excretion. There's a couple types of these oxidation reactions. One is oxidation of unactivated aliphatic carbon chains, and this is going to be, to me, it's almost one of the most interesting ones, because you cannot really do this in a laboratory setting. It's very difficult to just add a hydroxy group to a miscellaneous carbon almost. And then there's going to be oxidation of activated CH groups. So activated CH groups might have a next door benzene or something to kind of stabilize the CH position. And actually, it's actually going to activate or stabilize maybe a radical at the next door carbon. That's going to be the difference between unactivated and activated CHs. Alkene epoxidation, which you've learned about from organic 2 and organic 1, that we can epoxidize alkenes. Aromatic hydroxylation, we can attach hydroxy groups directly to benzenes. And then getting into the FMO enzymes, so the P450 are usually oxidizing, we'll say, carbons, and then FMO will directly oxidize things like nitrogen and sulfur. So this can be a little different. Okay, so let's talk about the oxidation of aliphatic chains, and by that we mean unactivated CHs. So there's two types of this that we often see. One is called omega oxidation, which means the kind of like the terminal methyl group or terminal group on an alkyl chain, and that'll oxidize that. Another one we see is omega -1 oxidation, which means one carbon from the end. So let's see an example. So this is ethosuximide. It's an anticonvulsant drug. So one of the metabolic products in the presence of P450 is the omega oxidation, which basically just attaches a hydroxy group to the end. And the omega -1 oxidation is hydroxy going to the next door carbon. So these probably happen because the chain sort of sticks into the P450 pocket, and then the terminal methyl could be oxidized. But so it's usually going to be omega and omega -1. Why do we call these maybe unactivated CHs? Because there's nothing to stabilize like a radical here. Like if it's a CH3 group, if I remove an H, then it would be a CH2 dot. And the CH2 dot is not stabilized by resonance that you might see like if there's a benzene here or something. And there's same thing with this. Neither of these positions is stabilized as a radical. So it's kind of weird. And like I said, I'm kind of fascinated by this because organic chemistry, like there's no way in the world I could take this molecule in the laboratory and do this. That's a very kind of like, it's a difficult process because there's no way to, there's nothing special about the CH3 and the CH2. I think in P450 it just kind of pokes into the pocket and then attaches. And the iron is able to do its metabolic process to attach the OH. And there probably is a radical involved in that. We didn't show like a radical intermediate in the mechanism, but most likely, an H dot is coming off. Then you have a carbon dot, and then the carbon dot is attaching to oxygen. Probably the last step in that mechanism we were showing, which, we're skipping some of the details. All right, cyclic aliphatic oxidation usually occurs at non-hindered positions, maybe on the opposite side of a ring. So this is perhexylene. It's a coronary vasodilator. P450 in this case attaches a hydroxy group randomly at this position on the cyclohexane, and you can imagine maybe here or there would be ideal locations for this. Let's talk about the oxidation of activated CH groups. So this means usually next to a pi bond, oxidation of a CH next to a pi bond. This kind of makes more sense because the pi bond can stabilize a radical intermediate. So this is a great example. P450 oxidizing this position next to the benzene to make the hydroxy group right there. And what we gave a name for this position. What did we give that name? The benzylic position. So benzylic refers to a carbon next door to a benzene. And also if we had a radical there, we'd call it a benzylic radical. And what's special about benzylic radicals, if I had a radical there, is I could draw a bunch of resonance structures where the radical delocalizes into the benzene, and then you have a new radical there. That radical can make a double bond there and make a new radical there. That radical could make a double bond there, make a new radical there. And anyway, it's a resonance stabilized benzylic radical. And so this is less surprising to me as an organic chemist than the last stuff, because this, at least we have radical stability at a place like this. So if the H is plucked off, you have a resonance stabilized radical. Also the case with this position next to an alkene. So P450 oxidizes this position to make an alcohol. And this also is a resonance stabilized radical position. When you take off the H and make a dot, the dot can delocalize with the alkene. Okay. If this is called benzylic, what's this called? This is called allylic. I think it's ALYLLIC, or I forgot where the L's are. You could Google that, allylic. Yeah. Okay. And so the allylic position is oxidized also by P450. And what about if next to an alkyne? Well, it's the same kind of rationale, that this is an activated position, and prone to oxidation due to radical stability. If this is benzylic and this is allylic, this is called propargylic, Propargylic, I think. Propargylic, okay? And all of these are due to a stabilized radical intermediate. And then the other situation is oxidation of a CH adjacent to a heteroatom. So like oxygen or nitrogen will also stable transient radical intermediate. Okay, so here's an example. So if I have R and then X being oxygen, nitrogen, or sulfur, P450 can oxidize this position. And the radical, if you imagine a radical, there is a resonance stabilization with the X group, and the lone pair can delocalize. So this is ultimately when this gets oxidized as a radical, this is transiently stabilized. And then alcohol gets introduced. And then the thing about an alcohol being introduced at this position next to the X group is that the alcohol can kick its electrons down and break off the bond, and we ultimately have a cleavage reaction. So this is a very common type of metabolism. It allows like it allows things like a propyl group, or very often methyl groups, like methyls, can be removed. We call this oxidative dealkylation. Okay, so the first step is an oxidation. The second step is not an oxidation. And it looks like, this is a aldehyde, higher oxidation state, but it's not. But this is not an oxidation. It's just when the oxygen is attached, its lone pair can kick down and break it off and make this kind of product. So this is still not an oxidation. First step's an oxidation. This is more of a cleavage reaction, a non-oxidative cleavage reaction. Okay, so let's show a couple specific examples of this. A couple specific examples. Okay, so oxidation of a CH adjacent to an amine. This will be one of the P450 kind of oxidative dealkylation reactions. So you can just imagine like propylamine, for example, as kind of a boring example of an amine getting oxidized where the carbon is. Now you have alcohol, and then the oxygen can kick down and kick off nitrogen, and now you have ammonia and propanol, the 3-carbon aldehyde. And if you have a secondary amine, the same kind of thing can happen, where the P450 oxidizes the carbon, and oxygen kicks down and kicks off nitrogen, and now you have a primary amine and the same aldehyde. So this is a case where essentially the propyl group just gets lost and dealkylated. So it's oxidative dealkylation. Okay. What about a tertiary amine? So the amine has 3 things on it. Same thing. You can easily lose an alkyl group by oxidizing the 3-carbon chain with P450. Oxygen kicks down, kicks off, and now you're left with a secondary amine. So in each of these cases, the alkyl chain just gets chopped off. As an example, diazepam, which is Valium, has a methyl group and this nitrogen. And as one of its oxidative pathways, the nitrogen methyl group gets hydroxylated to make this. And then the oxygen swings down, kicks off to make formaldehyde and the demethylated molecule. Okay. Also, do you guys know the name of this kind of intermediate? If you have a nitrogen and an oxygen, all of these have a name. I can't draw on this PowerPoint easily, but it's called a hemiaminal. Hemiaminal, Hemiaminal, hemiaminal. So each of these is going through this hemiaminal intermediate. We're going to see it, you see it from time to time in drug metabolism, so now you have a name for it, hemiaminal. Okay, oxidation of a CH next to an ether. So rather than cleaving an alkyl group off an amine, let's cleave it off an ether. Here is phenacetin. It's one of the early NSAID drugs, kind of like Tylenol or ibuprofen. And you have an ether there. What do you think might happen? What do you think might happen that might cause cleavage of the 2-carbon ether piece? Well, just like above, you can imagine hydroxylation at the position where the oxygen is, and then that can cleave off the ethyl group, and that's exactly what happens. So P450 oxidizes the carbon, and then you have this. If it was called a hemiaminal with nitrogen, this is called a hemiacetal with oxygen. So with nitrogen, it's a hemiaminal. And then this just falls apart. It cleaves, oxygen swings down, kicks this thing off, and now you're left actually with Tylenol. So this is an example of, this could actually be considered a prodrug because it's cleaving to generate an active metabolite, which is paracetamol or acetaminophen or Tylenol. Now, is this a useful prodrug strategy? I don't think it's actually used really, because Tylenol itself is also orally available, and it's a nice, easy to take drug. All right, so what about oxidative dehalogenation of aliphatic halides? So this is a case where we have halothane. It's a volatile anesthetic. It's one of these kind of gaseous anesthetic drugs that people take maybe during surgery. And anyway, so you can imagine, just like this position was a stable radical when the H got removed, and it did happen. It's just we're not showing that. Heme's doing that. But when you have a radical there, the next door thing stabilizes it. Well, the same thing happens here where you have the bromine and the chlorine. Both of them can stabilize a radical at this central position. And so oxidative dehalogenation will happen here. And P450 will cause hydroxylation at the middle position. And then the hydroxy group can kick in and probably kick off the Br or maybe the Cl. To make trifluoroacetyl, either chloride or bromide. And these are super reactive electrophiles, and this can be hydrolyzed to make trifluoroacetic acid, which is kind of toxic. Well, it's corrosive, but it's in small quantities, and it's going to be probably not that big of a deal in your body in small quantities. But this stuff is actually super reactive as an electrophile and can essentially acylate your liver proteins and cause liver toxicity. So this stuff is an okay anesthetic, but used over chronic periods of time can actually destroy your liver. And that's actually a problem with some of the other halogen-containing volatile anesthetics as well. Epoxidation of alkenes. Okay, so this is another oxidative reaction that can happen with P450. So here's one of these estrogen derivatives. I think it's an estrogen receptor agonist, diethyl stilbestrol. It's got an alkene in it, and alkenes are notorious for being epoxidized. And certainly, I think the alkene, anytime you have an alkene in between two benzenes, this is a very common reaction. And so P450 will epoxidize it. And and it's a way of oxidizing both carbons to generate the epoxide intermediate. Another case is carbamazepine, which is an anticonvulsant drug. The alkene is epoxidized by P450 to generate this epoxide. Sometimes that can cause severe toxicity as well because epoxides are electrophiles. And biological nucleophiles can attach to them. And if it's like DNA, that's really a problem. And it causes genotoxicity, which we have mentioned a couple times before, and especially when we're talking about toxicology. Here's an extreme example of that. This is called aflatoxin B. It's a fungal natural product, hepatocarcinogen. So this causes liver cancer. It's one of the most carcinogenic substances known. How is it carcinogenic? P450 epoxidizes this furan alkene. This is a DNA intercalator, so I think we've saw like camphothecin and some other DNA intercalators. Well, this now gets reacted to DNA and the N7 of guanosine. The DNA nucleophile will attack the epoxide and open it up, and that now you basically another situation of you've alkylated your DNA, and that is really bad. And so in your liver, your DNA attaches to this, and this also serves as an intercalator. So you have kind of a double effect, alkylation and intercalation, and this causes liver cancer. It's the mechanism of liver cancer for aflatoxin B. Aromatic hydroxylation is usually at the para position. So this is another oxidative reaction, but of benzenes, usually at the para position, least hindered site. So minoprene is an antidepressant, and hydroxylation occurs at the para position. And this is just it's a pretty simple example of P450 oxidation. And of course this is a more polar metabolite and would be more readily excreted. Like a lot of the previous examples, you're introducing a polar functionality. You're either introducing it and that can cause cleavage, or like in the dealkylation cases, you've dealkylated and that allows attachment of a conjugate, like a phase 2 reaction. So, but this is a case where the hydroxy group is just attached to the benzene. Electron poor rings are not oxidized, and this is actually something we can use to prevent ring metabolism in drugs. So in this case, the nitrogen has a lone pair that can kind of kick in to this benzene. The benzene we consider electron rich due to both of these nitrogens that can have, sort of electronically kick in. You can see it from here. Lone pair, kick in, make a double bond. This double bond goes there. This double bond goes there. And now we've added electron density. So this is called an electron rich benzene. But if you have an electron poor benzene, where maybe with an electron withdrawing group, then then that might prevent metabolism. So an example is probenicid. So this is a molecule with a benzene and 2 with electron withdrawing groups, carboxylic acid and then a sulfonamide thing. So the combination of these 2 electron withdrawing groups is sucking electrons from the benzene, and now it's an electron poor ring system. Okay, and it does not get hydroxylated. Here's a case where chlorpromazine, which is thorazine, it's an antipsychotic drug. We have a chlorine which Actually, so the chlorine does two things. One is it is a electron withdrawing substituent because it's electronegative. So it's pulling electrons towards it, and that makes the left side kind of electron poor. It also is sort of blocking this benzene because it's sort of a large thing. So the possible metabolic site is up here, but with this large atom up here, it's sort of blocking that site. Anyway, so due to this, and you know, the right side benzene is electron rich due to the sulfur and the nitrogen because they have lone pairs of electrons, and the lone pairs can kick into the benzene. This nitrogen lone pair can kick in also. So this benzene is electron rich. It also doesn't have anything blocking it. So P450 readily hydroxylates the right side benzene. Okay, so yeah, there's probably a double effect here. It's a blocking group, and it's also electron. You know, it's electronegative by induction. It's got a delta negative on it. Okay, let's talk about nitrogen sulfur direct oxidation now. And so what we saw before was this P450 catalyzed reaction. Typical example is hydroxylation next to a nitrogen, and then you have a hemiaminal. Let's remember that word, hemiaminal. Then the oxygen swings down, kicks it off. Now you've cleaved, and now you have a secondary amine and an aldehyde. Let's consider direct oxidation. So I think this is caused by FMO. And yeah, this is what we mean by direct oxidation of nitrogen or sulfur with FMO. And so in a tertiary amine, the lone pair of nitrogen kind of attacks an oxygen, electrophilic oxygen type atom, and then you get this system where it's N plus, and then we have this bond to O minus. And the arrow, that's a funny arrow. With this kind of bond between an N plus and a negatively charged, like oxygen, we often use this kind of bond. It's called a dative bond. Dative, D-A-T-I-V-E, dative bond. And we often use the funny arrow like this. Here's another case where an amide with two methyls on it is oxidized also by FMO to make the amide N oxide. This is an N oxide, a tertiary amine N oxide. This is a tertiary amide N oxide. This also happens with primary amines and also secondary amines with FMO. Now, they often don't form stabilized products. Primary and secondary N oxides are unstable, and usually something else happens. So while these might stop here, the bottom ones don't. They actually do some other metabolism. Also, another thing we see is sulfur do the same thing. So sulfur, like in the case of a sulfide, will oxidize with FMO to a sulfoxide. This is the dative bond equivalent of a sulfoxide. As we've shown sulfoxides before, there's two ways to show it. You can show it like this, S bound to O minus, S plus O minus. But we can also show it as a S double bond to O. And that is kind of the way you're probably used to seeing sulfoxides. And then it can happen again, and it can go from a sulfoxide to a sulfone. And this is like the doubly oxidized sulfur molecule. Okay, and also, this happens with FMO, not P450. Here's an example of this shows the mechanism of it. How does the mechanism actually occur? So these FMO enzymes initially react. Well, actually, I'll just I'll start at the top left. Okay, so the FMO enzymes have this flavin system. NADPH, like we said, is a reducing agent, and so the nitrogen kicks in, and the alkene shifts over, and then it transfers a hydride, an H minus. H minus gets delivered to the nitrogen, and then that kicks electrons all the way through the system, all the way over to the O minus here. So if there's first a reduction step due to NADPH, and then O minus swings all the way back, and then it attacks oxygen, molecular dioxygen. And now we have oxygen attached, and now the amine, like a substrate, R3N lone pair, for example, would attack this oxygen. So it's an electrophilic oxygen. Nitrogen lone pair attacks the oxygen, breaks the bond, and leaves you with an O minus. And that's the mechanism of how it works, how FMO works. And then you're left with your tertiary amine N oxide, and then you have a hydroxy group left over. Nitrogen lone pair can kick in and kick off the OH, and then you're just where you started. And then a new NADPH can join this process and start over. It's a nice catalytic cycle. It's pretty easy to see at the molecular level. Okay, so let's show a couple examples of the N-oxidation of a tertiary amine, which makes a stabilized N-oxide product. So this is guanethidine, or ismalin. It's an antihypertensive drug. It's got a nice tertiary amine there, and FMO causes the oxidation of the tertiary amine to the N-oxide, and this is the metabolic pathway for this molecule. Another one is cyproheptadine, or piracetin, which is an antihistamine. It's got a nice tertiary amine, and guess what happens with the tertiary amine? FMO reacts with it to make the N-oxide. Let's talk about secondary amines now. Like we said, secondary amines, when they are directly oxidized with FMO, will further react to make a different molecule, in this case a nitrone. So fenfluramine is an appetite suppressant. It was withdrawn from the US due to heart valve disease. It's a secondary amine, and FMO oxidizes it to the N-oxide. But then P450 will thereafter oxidize the carbon. So first we oxidize nitrogen, then we oxidize the carbon, and now the nitrogen kicks in and breaks off the hydroxy, and we get a nitrone functional group, which is kind of like a ketone, but with a nitrogen and an oxygen. So it's a different pathway. Totally different than a tertiary amine, because tertiary amines seem to stop at the tertiary amine N-oxide. All right, so let's talk about the direct oxidation of primary amines, and to show some of the weird subsequent reactivity that you might get with them. So it'll first oxidize on the nitrogen, and then it'll do something else. So here is D-L-amphetamine. DL refers to the stereochemistry. It's also called Adderall. And it is oxidized by FMO on the nitrogen, so it makes sort of an oxide or hydroxylamine type thing. And what can happen then is the base will take the proton and eliminate to make an imine. So you get this sort of imine intermediate. Well, one thing that can happen is that can be directly hydrolyze to the ketone, phenyl 2-propanone, and hydroxylamine. Actually, well, in this case it would be ammonia. So if water would hydrolyze this, then you need to get a ketone and you get ammonia out. But another option is that the imine can be oxidized with FMO also, and that makes the, I guess you'd say, N-hydroxyimine. It's also called an oxime. And then the oxime can also be hydrolyzed to the ketone, and that would actually give you hydroxylamine as a product, and that's how this would occur. And then another thing that can happen is that it can further oxidize on the nitrogen to like a double hydroxide functional group, and then that can rearrange to the nitro. So this just shows there's a lot of different byproducts you could get with, or oxidative metabolites you could get with this primary amine. Here is N-benzyl amphetamine, and this is a secondary amine, and this is maybe a little more easy to follow than the last one. P450, which generally oxidizes carbons, can oxidize the left carbon to make a hemiaminal. Remember that? And then the hemiaminal can kick down and kick off and to make phenylacetone and benzylamine. Another option is that the other side, the other carbon, can be oxidized with P450 to make this hemiaminal, and then the oxygen here would kick this off and kick off this nitrogen. So the mechanism is really simple. Lone pair kicks in, bond breaks, and breaks onto the nitrogen. Same with this one. Oxygen kicks in, and the bond breaks and goes to nitrogen. Okay. In this case, your products are a different amine. This is actually amphetamine, and benzaldehyde. Okay. And then we can also just directly oxidize the nitrogen to its N oxide, and then, like we saw before, there's another P450 would oxidize the carbon, and then we would get a nitron product. Okay, so a couple different pathways you can imagine here. Another example is nicotine. Now, nicotine does have nicotine does have a tertiary amine, and that can, cause, usually that just would allow an oxide formation with FMO, and that's actually what is shown down here. That's one thing that can happen. Another thing that can happen is that P450 can oxidize the right side CH to make this hemiaminal. And then P450 could oxidize that again, and these are known. I mean, this, and it's hard to predict this. On an assignment, I would probably give you some hints on how to do this. You can't. It's hard to just look at this and figure out what the metabolism is going to be. But given what the final metabolites are and the intermediates, you can usually figure this out. Okay, so yeah, we oxidize the right side CH to a hemiaminal. Then it oxidizes again to an amide. Then it oxidizes the left side CH to another hemiaminal. And then the oxygen kicks in, nitrogen kicks off, and you get this kind of ring open metabolite. So it's nicotine, in a pretty modified form. Okay. Another thing that can definitely happen, maybe the easiest thing, aside from the bottom, which is very easy too, but you could just demethylate the methyl group. And so P450 oxidizes the methyl to this hemiaminal. Oxygen kicks in, kicks off, and make nitrogen. And now you have a secondary amine and then formaldehyde. You could imagine this secondary amine could further react as well. I don't have evidence that happens, but it is feasible. Okay. Indirect oxidation for aromatic amines, which are anilines. This is a typical example. So an aromatic amine will react with... damn it. Will react with P450, which is weird because this is a direct oxidation and we're not using FMO. I think for aromatic amines, P450 is generally used metabolically. And then you get the hydroxylamine that's misspelled. So you get the N-hydroxy group. And then a typical example with aromatic amines is they will be acetylated or phase 2 metabolized. And then like DNA, I don't know why it's doing that. Sorry, my mouse is being funny. DNA will attack in a kind of a conjugate addition type thing, attack the alkene, and then the electrons form a double bond, and then this gets kicked off, and then there's an extra step that I'm not showing, which is that this CH gets removed, and then the electrons move around to make this. You can try to do that on your paper. But yeah, it's a two-step process. DNA attacks, and then we lose the proton right there, and then that forms this kind of thing. And this could lead to mutagenesis and cancer. For this reason, anilines are considered a toxicophore. So toxicophore means kind of like a part of the molecule that causes toxicity, or maybe mutagenesis, maybe cancer, maybe liver toxicity. So that's the word toxicophore. On occasion, anilines are found in non-toxic drugs, but often we in drug discovery, when we see an aniline as a potential drug, you might be warned that it might have toxicity, and because it has that toxicophore. Indirect oxidation. Okay, another example. Tylenol. Metabolism of Tylenol. Okay, so here's Tylenol, acetaminophen. So P450 again, in a kind of weird exception, that normally direct oxidation is done by FMO. In this case, P450 oxidizes the nitrogen to the hydroxylamine, the OH version. Then a base takes off the proton, and you form kind of a quinone type thing. So the double bond forms, this double bond transitions here, and then this double bond forms a C double bond N, hydroxy group goes away. And this is another kind of biological electrophile where a nucleophile might attack and be attached to this. Now, often your preferred biological nucleophile is glutathione, GSH, which would attack. Review the structure of it. It's got an SH, and the SH is nucleophilic. The SH, GSH, would attack the carbon and then kind of attach, kind of in this manner, and then you get GSH attacked, and that's great because that's excreted, right? But what if somebody maybe overdoses on Tylenol and they take a lot of it, maybe overwhelming your supplies of GSH? Well, then other nucleophiles might attack, like DNA, and then you'll have DNA attached to Tylenol. And it could be DNA, it could be liver proteins. Usually causes liver toxicity. Extreme cases, this is fatal, and a lot people overdose fatally on Tylenol, and this is kind of how that happens. It's usually due to not having enough glutathione as a nucleophilic scavenger. S-direct oxidation. The sulfides can be oxidatively cleaved just like amines with P450. So we're going to first do oxidative dealkylation, and then we'll do the direct oxidation. Okay, so like with P450, this is methotrol as a sedative, kind of in the, it almost looks like a barbiturate, like a thio, what is it? Kind of like thiopental or something like that. It's a barbiturate, and yeah, P450 could directly oxidize the CH3 group to make a thiohemiacetal or hemithioacetal. And then the oxygen kicks in, kicks off, and now you have the thiol. So this is a the kind of P450 deactivation of this molecule. Sulfur can also be oxidized by to sulfoxides and sulfones with FMO. So FMO as a direct oxidizing agent for the sulfur. And here's an example. This is kind of related to like chlorpromazine or some of the thiazine antipsychotics. In this case, FMO directly oxidizes the sulfur, both sulfurs, to make like a disulfoxide type thing. And that's different than the P450 mechanism. You know, it's a different metabolic system. And also, this is another one where we use FMO, not P450. And this is going from a sulfoxide to a sulfone functional group. Okay, and this is oxysuran immunosuppressant drug. Okay, I think for today we're going to stop. I'll continue with these phase 1 transformations, then go into phase 2 transformations next time, and then I think we'll transition into prodrugs, which is the next really cool section. Okay, well, hopefully this is interesting, and it shows, you know, how drugs are metabolized. They don't just stick around in your body. Your body is actively trying to excrete them, usually by some kind of reaction like this, and maybe dealkylation, and then later we'll see like a phase 2 conjugation, where something else will be attached and it'll be easily excreted. Okay. Anyway, have a great day.